Hello, my name is Matthew Hailemariam, and this is my Module 3 presentation for Psych 611. So if we want to test the association or underlying relationships of different variables, we'll use something called the general linear model, otherwise known as the GLM. And from the GLM, we can use two different processes. One is multiple regression / correlation, otherwise known as MRC, and the other one is analysis of variance, otherwise known as ANOVA. And using MRC and ANOVA, we can find y, which is our dependent variable, using x, which is our predictor, or can be a multiple predictors in a matrix of predictors. And we will also use b, which is the weight that is assigned to the predictor, and b0, which is the intercept, or what we expect y to be when there's no predictor present. And starting off, we'll specifically use multiple regression to find the unique variance shared between our dependent variable and each of multiple predictors of interest. And we can also use multiple regression to find any interaction between our predictors. And in addition, we can use multiple MRC to predict future occurrences or occurrences that will likely occur that we represent with y. And so we want to have the best linear unbiased estimates of population parameters with MRC. And to have this, we have several assumptions about the data that we use that helps make these best linear unbiased estimates. So first one is the theoretical relationship between our variables is correct, meaning that x is related to y in a rectilinear relationship and our predictors are independent. Then that there are no errors of commission, omission, or measurement, which means that we haven't included irrelevant variables and we haven't ignored relevant variables in our model. And we have measured our variables correctly. Another assumption is that the mean errors or residuals equal 0. That means for each observation, the average of the differences between an observation and the predicted group value should equal 0. And another is the variance is constant for all values of x, which is called homoscedasticity. And another one is errors are random and uncorrelated. Predictors are uncorrelated with errors, and errors are normally distributed. So here I have done a regression model that aims to predict y1, as you can see here, using the predictors x1, x2, and x3. And based on this model, it seems that neither one of my predictors is significant in predicting y1 because each of their p-values is above the significance threshold of 0.05. However, hypothetically, if these parameters were significant, then we can look at the estimates column and we could see the shared variance associated with each predictor, which again is the purpose of multiple regression. And it's also important to mention how to interpret this model correctly. For example, King mentions in his article that it's not possible to interpret accurate conclusions about the influence of another predictor on our outcome variable unless we also measure the predictor and include it in our full regression equation. And so we can run some diagnostics to check for any threats to the accuracy of our regression estimates. And a significant threat would be multicollinearity, or the degree to which our predictors are correlated. And we want low multicollinearity because high multicollinearity in a regression model leads to lower reliability of the estimates. And here I've created some bivariate plots of my predictors along with, and none of them seem too correlated except for x1 and x3, judging by the line of best fit. And we can also use these plots to find some outliers in our predictors that may be influencing the collinearity. And we can also use the variance inflation factors for each of our predictors to find signs of multicollinearity, which is what I've provided on the left. And this numerical value tells you in decimal form what percentage of the variance is inflated for each coefficient due to multicollinearity. And so in this case, the higher each VIF is, the more multicollinearity we have. So in this case, ours above 1 is seeming like moderate multicollinearity, but we only see that such a drastic change for x1. And you can also use a Cook's distance plot to find outliers that may be bringing in multicollinearity. And based on this plot that I have made right here, it seems that observation 14 and to a lesser extent observation 26 are some outliers that we may need to pay attention to. And we can also run some diagnostics to check for homoscedasticity, going back to our assumption that our residuals are normally distributed. And so based on these graphs, nothing seems to be out of order. Our top left graph is a plot of our residuals and fitted or predicted values. And in this case, we want the red line as close to 0 as possible. And it's pretty close from what I can tell. And the top right plot measures the normality of the distribution of our residuals demonstrated by this diagonal line. And most of them are on the line except for some of our outliers, as mentioned before. And Cortina, in his 2002 article, discusses how it may be tempting to just remove outliers like observation 14 that may be disproportionately influencing our model. But instead, we should first consider the appropriateness of removing said outlier from our model before we decide to remove it. And again, we see in our bottom two plots that observations 14 and 26 are outliers, and thus may be holding some leverage that is disproportionately influencing our results. And we can also run some more diagnostics to check for our other assumptions related to residuals. And we can see that the mean of our residuals is very close to 0, as you can see here. And each of our predictors seem to be uncorrelated with our residuals. And so that concludes the MRC portion of this presentation, but now we can talk about ANOVA, or analysis of variance. And so this also derives from the GLM, and this process is similar to the t-test, which compares the variance of two means using the t-statistic, but in ANOVA compares the variances of more than two means using the f-statistic. And ANOVA and MRC share several assumptions regarding residuals, and instead of residuals, we usually say error for ANOVA. And ANOVA and MRC also both use hypothesis testing, with the MRC null being R equals 0, and the ANOVA null being all group means are equal. In addition, we're also still using a parameter estimation in ANOVA as well, this time in the form of the within group variability and between group variability. However, there are some differences. Specifically, MRC uses covariates, and ANOVA uses class level predictors, or factors, which are grouping variables with levels. In addition, variance in ANOVA is also attributed to groups, while variance in MRC is attributed to individuals. And so some of the assumptions of ANOVA are that we still assume that we have independent errors, identically distributed errors, and normally distributed errors. So like I said before, ANOVA uses the f-statistic instead of the t-statistic, and the f-statistic is the ratio of the between group variance and within group variance, as you can see in this equation on the right. And so based on the output of the ANOVA model, it seems that the only factor that is significant is f2, due to its p-value being below our significance threshold of 0.05. And it turns out that neither f1 nor the interaction between f1 and f2 were significant. So we can only reject the null hypothesis for f2. And we can use the same plots as MRC for the ANOVA diagnostics. And some of the data in the plots look more vertical just due to the grouping of each predictors, as is the norm for ANOVA. And again, based on these plots, it seems that the residuals are pretty normally distributed, and there doesn't seem to be any significant recurring outliers. And here you can see my hand calculation for a bivariate MRC calculation. And here's my hand calculation for the ANOVA. And that concludes my presentation.